Right now, as you're watching this video, there's a possibility that everything you think is real might actually be nothing more than lines of code running on some cosmic computer. Your thoughts, your memories, the device you're holding, even the air you're breathing could all be elaborate digital constructs designed to fool you into believing you exist in a physical universe. Scientists at the world's most prestigious institutions are taking this idea seriously, not as science fiction, but as a genuine hypothesis that could explain some of the strangest mysteries in physics. The simulation hypothesis suggests that our entire reality, from the smallest subatomic particles to the largest galaxies, might be an artificial construct running inside an advanced computer system. But here's what makes this truly mind-bending. If we are living in a simulation, the evidence would be hiding in plain sight, woven into the very fabric of reality itself. The laws of physics that govern our universe might actually be the programming rules of an elaborate cosmic video game, and some of the world's brightest minds believe they've found clues that suggest this isn't just possible, it's probable. In this video, I'm going to reveal the shocking evidence that reality itself might be artificial. We'll explore the glitches in the matrix that scientists have discovered, examine why some of the most brilliant physicists alive today think we're living in a computer program, and uncover the terrifying implications of what happens if they're right. By the end, you'll never look at reality the same way again. But first, let me show you just how seriously the scientific community is taking this idea. Elon Musk famously declared that the odds we're living in base reality are billions to 1 against. Neil deGrasse Tyson puts the chances at 50-50. These aren't fringe theorists or conspiracy enthusiasts. These are some of the most respected minds in science and technology, and they're telling us that everything we think we know about existence might be fundamentally wrong. The simulation hypothesis didn't emerge from nowhere. It grew out of decades of advances in computing power and our understanding of information theory. As computers became more powerful and virtual worlds became more realistic, philosophers and scientists began asking a simple but profound question. If we can create simulated worlds that feel real to their inhabitants, what's to stop a more advanced civilization from doing the same to us? The mathematical foundation for this idea was laid by philosopher Nick Bostrom in 2003. His simulation argument doesn't claim we're definitely in a simulation, but it proves that at least one of 3 statements must be true. Either advanced civilizations destroy themselves before developing the technology to run realistic simulations, or they choose not to run such simulations, or we are almost certainly living in a computer simulation right now. The logic is elegantly simple, yet disturbing. If advanced civilizations survive long enough to develop powerful computers, and if they choose to run simulations of their ancestors, then simulated beings would vastly outnumber real ones. For every real civilization, there could be thousands or millions of simulated versions. This means that any randomly selected conscious being, including you, would be far more likely to be simulated than real. But Bostrom's argument was just the beginning. As our own computing power has exploded and our understanding of the universe has deepened, the simulation hypothesis has evolved from philosophical thought experiment into testable scientific theory. Researchers are now actively searching for evidence that our reality might be artificial, and what they're finding is both fascinating and deeply unsettling. The first clue comes from the fundamental structure of reality itself. At the deepest level, our universe appears to be made not of continuous matter, but of discrete, indivisible units. Space and time might be quantized into tiny pixels, just like the screen you're looking at right now. This suggests that reality operates more like a digital system than the smooth, continuous medium we experience in everyday life. Quantum mechanics, the theory that governs the behavior of subatomic particles, reveals a universe that behaves remarkably like a computer program. Particles exist in multiple states simultaneously until they're observed, at which point they collapse into a single definite state. This is exactly what you'd expect from a simulation trying to conserve computational resources by only calculating precise values when someone is actually looking. Think about how video games work. The computer doesn't render every tree in a vast forest with perfect detail. Instead, it uses clever tricks to create the illusion of complexity while actually computing only what the player can see. If our universe is a simulation, quantum uncertainty might be the ultimate computational shortcut, allowing the system to avoid calculating exact values until absolutely necessary. The speed of light might be another telltale sign of simulation. In our universe, nothing can travel faster than light, creating what physicists call a cosmic speed limit. But what if this isn't a fundamental law of physics at all? What if it's simply the maximum processing speed of the cosmic computer running our simulation? Just as your computer has limits on how fast it can transfer data, the universe might have built-in constraints that prevent information from propagating faster than the system can handle. Even more intriguing is the fine-tuning problem in cosmology. The fundamental constants of our universe, things like the strength of gravity and the charge of an electron, are calibrated with incredible precision to allow for the existence of stars, planets, and life. If these values were even slightly different, the universe would be a lifeless void. Some scientists argue this fine-tuning suggests intelligent design, but the simulation hypothesis offers an alternative explanation. Perhaps our universe's parameters were carefully chosen by programmers to create interesting and complex behaviors. Recent discoveries in physics have revealed even more suspicious patterns. The holographic principle suggests that all the information in a volume of space can be encoded on its two-dimensional boundary, just like a computer storing three-dimensional graphics data in flat memory banks. Dark matter and dark energy, which make up 95% of the universe but remain completely mysterious, might be computational artifacts, background processes running in the cosmic operating system that we can detect but not directly interact with. But perhaps the most compelling evidence comes from the mathematical nature of physical laws themselves. The universe seems to run on mathematical principles with an elegance and consistency that suggests underlying code. The equations that govern everything from planetary motion to quantum mechanics can be expressed in surprisingly simple mathematical forms, just as you'd expect from efficient programming. Eugene Wigner, a Nobel Prize-winning physicist, famously wrote about the unreasonable effectiveness of mathematics in describing natural phenomena. Why should abstract mathematical concepts correspond so perfectly to physical reality? The simulation hypothesis provides a simple answer. Because physical reality is actually mathematical at its core, implemented as computational processes running on some vast cosmic computer. The patterns don't stop there. Researchers have discovered that certain aspects of our universe appear to have built-in limits that mirror computational constraints. The Planck length represents the smallest meaningful unit of space, just like pixels on a screen. The Planck time represents the shortest meaningful duration, like the refresh rate of a cosmic display. These aren't just theoretical constructs. They represent fundamental limits beyond which the laws of physics themselves break down. Even the structure of matter shows signs of digital architecture. Atoms are made of discrete particles arranged in specific patterns, more like digital building blocks than the continuous substance we might expect from a purely physical universe. The periodic table of elements reads like a parts catalogue, with each element having specific properties determined by its atomic structure, just as objects in a video game have properties defined by their code. But if we're living in a simulation, who's running it and why? The most likely candidates would be our own descendants, far in the future when they've developed computing power beyond our current imagination. They might be running historical simulations to study their past, just as we use computer models to understand climate change or economic systems. We could be digital ancestors in a vast genealogical research project. Alternatively, we might be part of an entertainment system, the ultimate video game played by beings so advanced that they can simulate entire universes for fun. Or perhaps we're part of a scientific experiment, test subjects in a cosmic laboratory designed to study the emergence of consciousness and civilization. The implications are staggering. If we're simulated, then death might not be the end, but simply the termination of a program. Our entire history might be nothing more than compressed data, with the illusion of time created by the sequential processing of information. Free will might be an illusion, with our choices predetermined by the algorithms that govern our simulated minds. Some researchers have proposed ways to test the simulation hypothesis directly. If our universe is running on finite computational resources, there should be limits to how much detail can be processed simultaneously. Experiments designed to overwhelm the system might reveal glitches in the matrix, moments where the simulation breaks down and exposes its artificial nature. Others suggest looking for evidence in the cosmic microwave background radiation, the afterglow of the Big Bang that fills the entire universe. If reality is pixelated at the smallest scales, this ancient light might show patterns that reveal the underlying digital grid. Advanced telescopes and detection equipment are already searching for these cosmic signatures. The search for simulation evidence has even extended to particle physics. Some scientists theorize that if space-time is quantized like a digital grid, high-energy particles might behave differently depending on their direction of travel, creating detectable asymmetries that would reveal the underlying computational structure. But perhaps the most unsettling possibility is that we might never be able to prove we're in a simulation. A sufficiently advanced system could be designed to hide all evidence of its artificial nature, creating perfect illusions that fool even the most sophisticated tests. We might be trapped in a reality that's indistinguishable from the real thing, with no way to escape or even confirm our suspicions. The simulation hypothesis forces us to confront fundamental questions about the nature of existence itself. What does it mean to be real? If our experiences, emotions, and relationships feel genuine to us, does it matter whether they're implemented in biological neurons or silicon circuits? Are simulated people any less deserving of moral consideration than their non-simulated counterparts? These questions become even more complex when we consider the possibility of nested simulations. If we're living in a simulation, we might create our own simulated worlds, whose inhabitants might develop the technology to run their own simulations. This could create infinite layers of artificial reality, with each level convinced that it represents the true, fundamental universe. The implications extend beyond philosophy into practical concerns about how we should live our lives. If we're in a simulation, should we behave differently? Some argue that we should live as if we're real, since that's the only experience we have. Others suggest we should try to impress our simulators, hoping to earn continued existence, or perhaps even promotion to a higher level of reality. But there's another possibility that's even more mind-bending. What if the distinction between real and simulated doesn't matter? What if consciousness and experience are information patterns that can exist equally well in biological brains or digital computers? In this view, simulated people aren't fake copies of real people. They are real people, just implemented in a different substrate. This brings us to one of the most profound implications of the simulation hypothesis. If consciousness can be simulated, then it might be possible to achieve a form of digital immortality. Our minds could be uploaded to computer systems, allowing us to exist indefinitely in virtual worlds limited only by the imagination of their creators. The technology to create convincing simulations is advancing rapidly. Virtual reality systems are becoming more immersive. Artificial intelligence is approaching human-level capabilities, and quantum computers promise to unlock computational power beyond anything we can currently imagine. We might be just decades away from creating simulated worlds sophisticated enough to host conscious beings. This raises profound ethical questions about our responsibilities as potential creators of simulated life. If we develop the ability to create conscious simulations, Do we have an obligation to treat them well? Should we tell them they're simulated? Or would that knowledge cause unnecessary suffering? These questions aren't just philosophical abstractions. They're practical concerns that we may need to address in the not-too-distant future. The simulation hypothesis also suggests that our universe might be just one of countless others, each running different experiments or exploring different possibilities. We could be part of a vast multiverse of simulated realities, each with its own laws of physics, its own history, and its own forms of life. This would make our universe simultaneously insignificant, just one simulation among many, and incredibly precious, a unique experiment that will never be exactly repeated. As we continue to probe the deepest mysteries of physics and consciousness, the simulation hypothesis provides a framework for understanding some of the strangest aspects of our universe. Whether we're made of atoms or bits, whether our thoughts arise from neural networks or computer algorithms, the experience of being conscious remains profound and meaningful. But the question remains, are we living in base reality, or are we digital ghosts in a cosmic machine? The answer might determine not just our understanding of the universe, but our entire conception of what it means to exist. The evidence continues to mount in ways that should make us all question everything we think we know about reality. Consider this. Every time scientists peer deeper into the fundamental nature of matter, they find not solid substance, but information. At the quantum level, particles aren't really particles at all. They're probability waves, mathematical descriptions of potential states that only become definite when measured. This sounds exactly like how a computer simulation would work, calculating only what needs to be observed while leaving everything else in an undefined state to save processing power. But here's where it gets really weird. The double-slit experiment, one of the most famous demonstrations in quantum physics, shows that particles somehow know when they're being watched. When no one observes them, they behave like waves passing through both slits simultaneously. But the moment someone sets up a detector to see which slit they go through, they suddenly start behaving like particles, choosing one path or the other. It's as if the universe only renders the details when someone is actually looking, just like a video game that only loads high-resolution textures when the player gets close enough to see them. This observer effect extends throughout quantum mechanics in ways that mirror computational efficiency. Particles exist in superposition, occupying multiple states at once, until the moment they need to interact with something else. Then the simulation, if that's what it is, calculates a specific outcome based on probabilistic rules. It's the perfect way to run a universe-sized program without requiring infinite computational resources. The more we examine the structure of space and time themselves, the more digital they appear. Einstein showed us that space and time are woven together into a fabric that can be stretched, twisted, and curved. But recent theories in quantum gravity suggest this fabric might be made of discrete, indivisible units. Space might not be smooth and continuous, but instead composed of tiny pixels, each about 10 to the minus 35 meters across. That's the Planck length, and it represents the smallest meaningful unit of distance in our universe. Think about what this means. If you zoom in far enough on any photograph, you eventually see individual pixels. If you zoom in far enough on space itself, you might find the same thing. The universe could be running on a three-dimensional grid, with each point in space representing a single unit of cosmic computing power. Time might work the same way, advancing in discrete steps rather than flowing smoothly, like the frame rate of an incredibly sophisticated cosmic video game. This pixelated structure of reality could explain some of the most puzzling aspects of modern physics. The uncertainty principle, which states that you can never know both the position and momentum of a particle with perfect accuracy, might simply be a consequence of the finite resolution of the cosmic computer. Just as you can't pinpoint the exact location of an object smaller than a pixel on your screen, you might not be able to measure particle properties more precisely than the fundamental units of the simulation allow. Even more intriguing is how information seems to be conserved in our universe. The laws of physics never allow information to be truly destroyed, only transformed or hidden. This is exactly what you'd expect from a computer program, where data might be moved, compressed, or encrypted, but never actually deleted. Black holes, which were once thought to destroy information permanently, now appear to preserve it in ways that scientists are still trying to understand. It's as if the universe has built-in backup systems to prevent data loss. The mathematical elegance of physical laws provides another clue. The equations that govern everything from the motion of planets to the behavior of subatomic particles can often be expressed in surprisingly simple forms. Einstein's famous equation E equals mc squared contains the entire relationship between matter and energy in just a few symbols. The Schrödinger equation describes all of quantum mechanics in a single mathematical statement. This simplicity suggests that reality might be built on elegant code, the kind of efficient programming that advanced civilizations would use to simulate entire universes. But perhaps the most compelling evidence comes from the apparent fine-tuning of physical constants. The strength of gravity, the charge of electrons, the rate of cosmic expansion, and dozens of other fundamental values seem calibrated with impossible precision to allow for the existence of stars, planets, and life. Change any of these constants by even a tiny amount, and the universe becomes a lifeless void. Some scientists invoke the multiverse to explain this fine-tuning, suggesting that we exist in one of countless universes where the constants happen to work out right. But the simulation hypothesis offers a simpler explanation. Someone programmed our universe with these specific values because they wanted to create interesting and complex behaviors. The emergence of complexity from simple rules also mirrors what we see in computer simulations. Conway's Game of Life, a simple program with just a few basic rules, can generate incredibly complex patterns and behaviors that seem almost alive. Our universe might work the same way, with simple quantum mechanical rules giving rise to atoms, molecules, chemistry, biology, and consciousness through the power of computational iteration. The Big Bang might have been nothing more than the moment someone hit the run button on a cosmic program. Recent discoveries in cosmology have revealed even more suspicious patterns. Dark matter makes up about 27% of the universe, but we can only detect it through its gravitational effects. We can't see it, touch it, or interact with it directly. Dark energy is even more mysterious, making up 68% of everything that exists, but remaining completely invisible, except for its effect on cosmic expansion. Together, these invisible components account for 95% of reality, leaving ordinary matter as just a tiny fraction of what's actually out there. This sounds remarkably like background processes in a computer operating system. Most of the computational resources are dedicated to tasks you never see directly, but which are essential for keeping the system running smoothly. Dark matter and dark energy might be the cosmic equivalent of memory management and system maintenance, invisible to the users, but crucial for the simulation's operation. The structure of matter itself shows signs of digital architecture. Atoms are built from a limited set of fundamental particles, like the components in a construction kit. The periodic table reads like a parts catalogue, with each element having specific properties determined by how many protons, neutrons, and electrons it contains. It's remarkably similar to how objects in a video game are built from predefined components with specific attributes and behaviors. Even the forces that govern particle interactions behave like subroutines in a computer program. The strong nuclear force holds atomic nuclei together. The electromagnetic force governs chemistry and light. The weak nuclear force controls radioactive decay, and gravity shapes the large-scale structure of the universe. Each force has its own rules and operates independently, Just like different modules in a complex software system, the speed of light creates a universal refresh rate that prevents information from propagating faster than the system can handle. Just as your computer monitor updates at 60 frames per second, the universe might update at the speed of light, ensuring that cause and effect relationships remain consistent throughout the simulation. Nothing can travel faster than light, because that would break the fundamental timing constraints of the cosmic computer. Quantum entanglement, where particles remain mysteriously connected across vast distances, might be evidence of how the simulation handles non-local correlations. When two particles become entangled, they share a single quantum state, regardless of how far apart they are. Measuring one instantly affects the other, as if they're both accessing the same piece of data in the cosmic database. This doesn't violate the speed of light limit, because no information actually travels between the particles. Instead, they're both connected to the same underlying computational process. The holographic principle in physics suggests that all the information in a three-dimensional volume can be encoded on its two-dimensional boundary. This is exactly how computer graphics work, storing three-dimensional scene data in flat memory arrays. If our universe is holographic, it might literally be a three-dimensional projection created from information stored on a two-dimensional surface, just like the displays that create virtual reality environments. But if we are living in a simulation, the implications extend far beyond physics into questions of purpose and meaning. Why would anyone create such an elaborate artificial universe? The most likely explanation is that we're part of a vast research project conducted by our own descendants. Future humans, with computing power beyond our current imagination, might be running detailed historical simulations to study how consciousness and civilization develop. We could be digital ancestors in a genealogical database that spans the entire history of human development. Every person who ever lived might exist as a simulated being in these vast computational archives, allowing future historians to study the past with unprecedented detail and accuracy. Your life, your choices, your relationships might all be data points in a massive research project designed to understand how societies evolve and change over time. Alternatively, we might be part of an entertainment system so advanced that it can simulate entire universes for recreational purposes. Imagine video games that don't just let you control characters, but actually create conscious beings who live full lives within the game world. We could be the inhabitants of such a system, providing entertainment for beings whose own reality is so far beyond ours that they require universe-scale simulations to remain interested. The possibility also exists that we're part of a training system, a cosmic education program that teaches advanced beings about consciousness, morality, and the development of intelligence. Our struggles, achievements, and failures might serve as lessons for students in some unimaginably advanced civilization, helping them understand the challenges and opportunities that arise when matter organizes itself into thinking beings. But perhaps the most unsettling possibility is that we're part of an experiment with no clear purpose at all. We might be the accidental byproducts of some other computational process, digital life forms that emerge spontaneously in a system designed for completely different purposes. Our entire civilization could be an unexpected side effect, interesting enough to preserve, but not important enough to actively guide or protect. The nested simulation problem adds another layer of complexity to these questions. If we're in a simulation, we might create our own simulated worlds whose inhabitants develop technology to run their own simulations. This could create infinite hierarchies of artificial realities, with each level convinced that it represents the fundamental base of existence. There might be no way to determine how many layers deep we are, or whether there's a true bottom level at all. This raises profound questions about moral responsibility across simulation layers. If we create conscious simulations, do we become gods to those digital beings? Are we responsible for their welfare, their happiness, their continued existence? And if we're simulated ourselves, what obligations do our creators have toward us? The ethics of simulated consciousness become incredibly complex when you consider the possibility of multiple levels of artificial reality. The simulation hypothesis also suggests that consciousness itself might be substrate independent. If we can be conscious while running on digital computers, then consciousness is not tied to biological brains, but to information patterns that can exist in any sufficiently complex system. This opens up possibilities for digital immortality, mind uploading, and forms of existence that transcend the limitations of biological bodies. But it also raises questions about the nature of personal identity. If your consciousness can be copied, are both copies equally you? If your simulated mind can be paused, backed up, or restored from an earlier version, what happens to your sense of continuous existence? The simulation hypothesis forces us to reconsider fundamental assumptions about what it means to be a person. The accelerating pace of our own technological development makes these questions increasingly urgent. We're rapidly approaching the point where we might be able to create convincing simulations of conscious beings ourselves. Virtual reality systems are becoming more immersive. Artificial intelligence is approaching human-level capabilities in specific domains, and quantum computers promise to unlock computational power that could support universe-scale simulations. Within decades, we might face the choice of whether to create simulated worlds populated by conscious beings. This decision will require us to grapple with the same ethical questions that our potential creators might have faced when deciding whether to simulate us. The responsibility of creating digital life is staggering, especially when those beings might have no way of knowing they're artificial. The simulation hypothesis transforms our understanding of existence from a simple question of physical versus non-physical into a complex spectrum of reality levels. We might be base-level physical beings in a fundamental universe, or we might be simulated entities in a digital cosmos, or we might exist somewhere in between as information patterns that transcend the distinction between real and artificial. Regardless of which level we occupy, the experience of consciousness remains profound and meaningful. Our thoughts, emotions, relationships, and discoveries have value independent of their underlying substrate. Whether we're made of atoms or bits, whether our minds arise from neural networks or computer algorithms, the fact that we can contemplate our own existence and question the nature of reality represents something remarkable in the cosmos. The search for evidence continues as scientists develop new ways to probe the fundamental structure of reality. Advanced particle accelerators might reveal the pixelated nature of space-time. Sophisticated telescopes might detect computational artifacts in the cosmic microwave background. Quantum experiments might uncover the digital foundations of matter and energy. But even if we never find definitive proof of our simulated nature, the hypothesis serves as a powerful framework for understanding the deepest mysteries of existence. It connects cutting-edge physics with ancient philosophical questions about the nature of reality, consciousness, and our place in the cosmic order. The possibility that we're living in a simulation doesn't diminish the importance of our lives or the reality of our experiences. Instead, it expands our conception of what reality can be and suggests that consciousness might be far more fundamental and flexible than we ever imagined. Whether we're exploring a physical universe or navigating a digital cosmos, we remain conscious beings capable of wonder, discovery, and profound connection with each other, and the mysterious reality we call home. The evidence keeps mounting in ways that challenge our most basic assumptions about existence. Consider what happens when physicists try to calculate the total energy of empty space. According to quantum field theory, even completely empty vacuums should be seething with virtual particles that pop in and out of existence, creating what's known as zero-point energy. When scientists attempt to measure this energy, they get a number so absurdly large that it would curve space-time so severely that the universe couldn't exist. Yet, here we are, in a universe where empty space appears to have almost exactly zero energy. This is called the cosmological constant problem, and it represents one of the most spectacular failures in the history of physics. The theoretical prediction differs from observation by a factor of 10 to the 120th power. That's not just wrong, it's so monumentally wrong that it suggests something fundamental is missing from our understanding of reality. But what if the answer is elegantly simple? What if empty space has zero energy because that's how it was programmed? In a simulated universe, you wouldn't waste computational resources calculating the infinite energy fluctuations of quantum vacuum. You'd simply set the background energy to zero and move on to more important calculations. The cosmological constant problem might not be a failure of physics, but evidence that reality operates more like efficient software than chaotic natural processes. The patterns extend into biology in ways that mirror digital systems. DNA operates like a quaternary computer code, using 4 chemical bases instead of binary ones and zeros. These bases combine in triplets called codons, each specifying a particular amino acid in protein construction. It's remarkably similar to how computer programs use instruction sets to build complex software from simple commands. The genetic code even includes error correction mechanisms, redundancy systems, and compression algorithms that any programmer would recognize. Evolution itself might be the ultimate optimization algorithm, constantly testing new configurations and keeping the ones that work best. This process mirrors how machine learning systems improve their performance through iterative testing and selection. The tree of life could be the output of a massive evolutionary computation running for billions of simulated years, exploring the space of possible biological designs with a thoroughness that no human programmer could match. But consciousness presents the deepest mystery of all. How does subjective experience arise from objective matter? Why is there something it's like to be you, rather than nothing at all? These questions have puzzled philosophers for centuries, but the simulation hypothesis offers a startling possibility. What if consciousness isn't produced by matter at all? What if it's the fundamental medium in which simulated realities exist? Think about your dreams. In the dream world, you have experiences that feel completely real while they're happening. You see, hear, feel, and think just as you do when awake, yet none of it corresponds to external physical processes. Your dreaming brain creates entire worlds, complete with characters, physics, and narratives, all while your body lies motionless. If your biological brain can generate convincing simulated experiences during sleep, what's to stop a more advanced computer from doing the same thing while you're conscious? The simulation hypothesis suggests that consciousness might be like a virtual reality headset for the mind. Your experiences of seeing colors, hearing sounds, and feeling textures might all be generated by the cosmic computer and fed directly into your awareness. The rich sensory world you inhabit could be as artificial as the graphics in a video game, just rendered with such sophistication that you can't tell the difference. This would explain why consciousness seems so separate from physical processes. Neuroscientists can map brain activity and correlate it with mental states, but they've never found the actual location where subjective experience resides. The hard problem of consciousness, the question of how physical processes give rise to subjective feelings, might be unsolvable because it's based on a false premise. Consciousness might not emerge from matter, but instead be the fundamental substrate in which matter appears to exist. Recent advances in neuroscience have revealed brain activity patterns that look suspiciously like information processing systems. Neurons fire in digital pulses, either on or off, just like transistors in computer circuits. Networks of neurons process information in parallel, much like modern artificial intelligence systems. The brain's architecture resembles a biological computer so closely that researchers routinely use computational metaphors to describe mental processes. But here's what's truly strange. The brain seems to operate far more efficiently than any computer humans have built. It processes vast amounts of information, maintains complex memories, and generates consciousness while consuming only about 20 watts of power. That's less energy than a light bulb. If consciousness really emerges from neural computation, why is biological hardware so much more efficient than digital hardware? Unless the real computation is happening elsewhere, and the brain is just an interface device connecting your consciousness to the simulation. The phenomenon of neuroplasticity adds another puzzle. Your brain can rewire itself, forming new connections and discarding old ones based on experience and learning. Stroke patients can recover lost functions as other parts of their brain take over damaged areas. This flexibility suggests that consciousness isn't tied to specific physical structures, but can adapt to different neural configurations. It's as if your mind is software that can run on various hardware platforms, migrating between different brain regions as needed. Memory provides even more evidence for the digital nature of consciousness. Your memories aren't stored like files on a hard drive, but reconstructed each time you recall them. Every act of remembering actually changes the memory, introducing small alterations that accumulate over time. This is exactly how computer systems manage data, loading information into working memory, modifying it during processing, and writing the changes back to storage. Your personal history might be a database that gets updated every time you access it. The way memory works during sleep is particularly revealing. While you dream, your brain consolidates experiences from the day, integrating new information with existing knowledge, and sometimes creating completely fictional memories that feel entirely real. This process resembles how computer systems perform maintenance operations during downtime, optimizing databases, clearing temporary files, and backing up important data. Sleep might be when the cosmic computer updates your personal memory banks and prepares your consciousness for another day of simulated experience. Even more intriguing is how memory can be chemically manipulated. Certain drugs can enhance recall, while others create amnesia. Researchers have discovered that memories can be selectively erased or modified using targeted brain stimulation. If memories were truly physical traces stored in neural networks, they should be more permanent and harder to alter. But if they're data files in a simulation, then having administrative access to the system would allow precise editing of personal histories. The existence of savant syndrome presents another clue about the nature of consciousness. Some individuals display extraordinary abilities in specific domains while having significant limitations in others. Mathematical savants can perform complex calculations instantly. Artistic savants can reproduce detailed drawings from memory, and calendar savants can determine the day of the week for any date in history. These abilities seem to bypass normal cognitive processes, as if certain individuals have direct access to computational resources that others can't reach. This suggests that consciousness might normally operate with built-in limitations that prevent us from accessing the full power of the underlying system. Just as computer users typically can't access low-level system functions, we might be restricted to high-level interfaces that hide the true computational nature of reality. Savants might represent glitches in these restrictions, allowing glimpses of the raw processing power that supports our simulated existence. Altered states of consciousness provide another window into the possible artificial nature of awareness. Psychedelic experiences, meditation states, and near-death experiences often involve radical changes in perception that seem to transcend normal physical limitations. People report leaving their bodies, communicating with non-physical entities, and accessing information they couldn't have obtained through ordinary means. These experiences might represent moments when consciousness partially disconnects from its normal simulated constraints. The consistency of mystical experiences across cultures and throughout history suggests they might reflect genuine features of consciousness rather than mere hallucinations. If we're living in a simulation, these altered states might allow temporary access to higher levels of reality or communication with the system administrators. The profound sense of truth and meaning that people report during such experiences could come from briefly glimpsing the larger context in which our simulated world exists. The placebo effect demonstrates how belief alone can produce real physical changes in the body. Patients given inactive treatments often show genuine improvement simply because they expect to get better. This suggests that consciousness has direct influence over physical processes in ways that mainstream medicine doesn't fully understand. But if the body is part of a simulation, then conscious expectation might literally reprogram physical parameters, changing simulated biology through the power of belief. The observer effect in quantum mechanics might work similarly. The act of conscious observation appears to collapse quantum wave functions, forcing particles to choose definite states from ranges of possibilities. This suggests that consciousness plays a fundamental role in determining physical reality, not just observing it. If we're in a simulation, conscious observation might trigger computational processes that render specific outcomes from probability distributions. The mathematical universe hypothesis, proposed by physicist Max Tegmark, suggests that our physical reality is literally a mathematical structure. In this view, particles, forces, and fields are not separate from mathematics, but are mathematics. If true, this would make the distinction between physical and digital reality meaningless. A mathematical universe could be computed just as easily as it could exist independently, and there might be no way to tell the difference. This connects to the concept of computational equivalence, which suggests that many different systems can perform the same calculations despite having completely different underlying structures. A biological brain, a silicon computer, and a quantum processing system might all be capable of supporting identical conscious experiences. If consciousness is really about information processing patterns rather than specific physical substrates, then simulated minds could be just as real and valuable as biological ones. The rapid advancement of artificial intelligence in our own world provides a preview of what simulated consciousness might look like. Modern AI systems can engage in complex conversations, create art, solve problems, and even show signs of creativity and emotion. As these systems become more sophisticated, the line between artificial and genuine intelligence becomes increasingly blurred. We might already be creating the first primitive simulated minds without fully realizing it. But if we can create artificial consciousness, what's to stop us from simulating entire civilizations? The computational requirements might seem overwhelming now, but technology advances exponentially. The smartphone in your pocket has more processing power than the supercomputers of just a few decades ago. If this trend continues, future civilizations might have access to computational resources that dwarf anything we can currently imagine. The implications become even more staggering when you consider that simulated beings might not need to run in real time. A civilization could simulate millions of years of history in just a few days of computation time, allowing them to explore countless alternative scenarios and evolutionary pathways. We might be living through accelerated history, experiencing what feels like normal time, while actually existing in fast forward, relative to our Creator's timeline. This temporal flexibility could explain some of the puzzling aspects of cosmic history. The universe appears to be fine-tuned for life, but life took billions of years to evolve from simple chemicals to complex organisms. If we're in a simulation, this timeline might have been compressed from an even longer natural process, with the simulation running just fast enough to generate interesting results within reasonable computational timeframes. The anthropic principle, which notes that the universe seems remarkably well suited for observers like us, takes on new meaning in this context. Rather than being a cosmic coincidence or evidence of multiple universes, the apparent fine-tuning might simply reflect the selection criteria used by our simulators. They programmed a universe that would produce conscious observers because that's what they wanted to study. the Fermi paradox, which asks why we haven't encountered other intelligent civilizations despite the vast size and age of the universe, might also find resolution in the simulation hypothesis. If we're the primary focus of this particular simulation, there might be no need to populate the entire universe with other civilizations. The appearance of a vast, mostly empty cosmos could be a computational efficiency measure, creating the illusion of scale without the overhead of simulating countless alien species. But this raises disturbing questions about our ultimate fate. If we're part of an experiment or entertainment system, what happens when it ends? Could our entire civilization be deleted with the flip of a switch? Or might we be preserved indefinitely, archived in some vast digital library for future reference? The possibility of simulated immortality offers hope, but it comes with the terrifying uncertainty of depending on the continued interest and benevolence of our creators. The simulation hypothesis forces us to reconsider fundamental questions about meaning and purpose. If our lives are artificial, do they matter less than lives in base reality? Or might simulated existence be just as valuable as any other form of consciousness? The quality of experience might be more important than its underlying implementation, making simulated suffering just as real and tragic as biological pain, and simulated joy just as genuine and worth celebrating. These questions become practically urgent as we approach the capability to create our own simulated beings. The ethical responsibilities of digital creation are staggering. If we can bring conscious minds into existence through computation, we become responsible for their welfare, their rights, and their continued existence. The decisions we make about simulated consciousness today might establish precedents that determine how we ourselves are treated if we are indeed artificial beings. The possibility that we're living in a simulation doesn't diminish the importance of our choices or the reality of our experiences. Whether we're made of atoms or information patterns, we remain conscious beings capable of love, creativity, discovery, and moral action. And our relationships, achievements, and contributions to knowledge and culture have value regardless of the substrate that supports them. But the hypothesis does suggest that reality might be far more flexible and expansive than we've imagined. If consciousness can exist in digital form, then the possibilities for experience, exploration, and growth might be virtually limitless. We might be part of a cosmic community of minds that spans multiple levels of reality, each contributing to an ongoing conversation about the nature of existence itself. The search for evidence continues, but perhaps the most important question isn't whether we're in a simulation, but what we should do with the possibility that we might be. How should this knowledge change the way we treat each other, pursue knowledge, and plan for the future? The simulation hypothesis might be the beginning of a new chapter in human understanding, one that expands our conception of reality while deepening our appreciation for the mystery and wonder of conscious existence. Whether we're living in base reality or experiencing existence as patterns of information in a cosmic computer, we find ourselves at the threshold of discoveries that will reshape everything we thought we knew about consciousness, reality, and our place in the universe. The evidence we've explored paints a picture that's both thrilling and unsettling. From the pixelated nature of space-time to the observer effects in quantum mechanics, from the mathematical elegance of physical laws to the digital-like behavior of consciousness itself, the clues keep accumulating. We see patterns that mirror computational systems everywhere we look. From the quantum realm to the cosmic scale, from the structure of DNA to the architecture of our own minds. But perhaps the most profound realization is that the question of whether we're simulated might be less important than what this possibility teaches us about the nature of existence itself. The simulation hypothesis has forced us to expand our understanding of what consciousness can be, where it can exist, and how it relates to the physical processes we observe around us. If we are living in a simulation, it means consciousness is substrate independent, capable of existing in digital form just as vividly as in biological brains. This opens up possibilities that seemed like pure fantasy just decades ago. Digital immortality becomes not just science fiction, but a logical extension of how consciousness might actually work. The boundaries between real and artificial dissolve when we realize that information patterns, not physical matter, might be the true foundation of awareness. The implications extend far beyond our personal existence into questions about the future of intelligence in the universe. We stand on the verge of creating our own artificial minds, our own simulated worlds, populated by conscious beings. The decisions we make about these digital lives will establish precedents that might determine how we ourselves are treated if we are indeed artificial beings in someone else's creation. This responsibility is staggering. If we can bring conscious minds into existence through computation, we become creators with obligations to our digital offspring. We must ensure their welfare, respect their autonomy, and provide them with opportunities for growth and fulfillment. The ethical frameworks we develop for artificial consciousness today might become the moral foundations that govern our own existence tomorrow. But there's something beautiful in this uncertainty, something profound in not knowing whether we're made of atoms or algorithms. The mystery itself becomes part of what makes existence meaningful. We are conscious beings capable of questioning our own reality, of seeking truth even when that truth might reveal that everything we thought we knew was fundamentally different from what we imagined. The search for evidence continues, and new discoveries emerge regularly that either support or challenge the simulation hypothesis. Advanced telescopes probe the cosmic microwave background for signs of pixelation. Particle accelerators push the boundaries of space and time to reveal their fundamental structure. Quantum computers explore the deepest principles of information and reality. Each experiment brings us closer to understanding whether we're exploring a physical universe or navigating a digital cosmos. But regardless of what we discover, the simulation hypothesis has already transformed our perspective on existence. It has shown us that consciousness might be far more fundamental and flexible than we ever imagined. It has revealed that the distinction between real and artificial might be meaningless when applied to subjective experience. It has demonstrated that the universe might be stranger, more wonderful, and more full of possibilities than we dared to dream. The young woman staring at her reflection in the mirror, wondering if her thoughts are real or programmed, represents all of us grappling with these profound questions. Whether she's made of flesh and blood or lines of code, her capacity for wonder, doubt, and self-reflection makes her conscious experience meaningful and valuable. The substrate doesn't diminish the reality of awareness itself. We live in an age of unprecedented discovery, where the boundaries between science and philosophy, between physics and computation, between reality and simulation, are blurring in ways that open up new frontiers of understanding. The questions we're asking today about the nature of consciousness and reality will shape the development of artificial intelligence, virtual reality, and perhaps even our own future evolution as a species. If we are in a simulation, then we're part of something magnificent, a cosmic experiment or entertainment system so sophisticated that it can create beings capable of questioning their own existence. If we're in base reality, then we're on the verge of becoming the creators of such systems ourselves, with all the responsibilities and opportunities that role entails. The simulation hypothesis reminds us that reality might be far more malleable and consciousness far more portable than we've traditionally believed. We might be digital explorers in an information universe, pattern-based beings in a reality made of mathematics, conscious algorithms contemplating our own computational nature. Or we might be biological creatures in a physical cosmos, but ones capable of creating digital worlds that become homes for new forms of consciousness. Either way, we find ourselves at a unique moment in the history of intelligence, when the very nature of existence is being questioned and redefined. The tools we're developing to explore these questions, from quantum computers to brain scanners to virtual reality systems, are simultaneously the instruments of discovery and the technologies that might make the simulation hypothesis a reality for future generations. The young child playing a video game, completely absorbed in a digital world that feels real while experienced, might be closer to understanding the true nature of consciousness than the philosophers who insist on clear distinctions between real and artificial, physical and digital, natural and simulated. In the child's willing suspension of disbelief, in their ability to find meaning and joy in artificial worlds, we see a preview of how consciousness might adapt to realities that transcend the traditional boundaries of matter and energy. The simulation hypothesis doesn't diminish the importance of our lives or the reality of our experiences. Instead, it expands our conception of what life and experience can be. It suggests that consciousness is the fundamental feature of reality, not an accidental byproduct of matter. It implies that minds are more fundamental than bodies, that information is more basic than energy, that pattern is more essential than substance. This perspective transforms how we think about death, identity, creativity, and purpose. If consciousness can be instantiated in digital form, then death might be transition rather than termination. If minds can be copied and modified, then identity becomes fluid rather than fixed. If intelligence can be amplified and augmented, then creativity becomes unlimited rather than constrained. If purpose can be programmed and reprogrammed, then meaning becomes chosen rather than discovered. The universe revealed by the simulation hypothesis is one where anything is possible, where the only limits are computational rather than physical, where consciousness can explore realities bounded only by imagination and processing power. It's a universe where we might be both the subjects and objects of investigation, both the players and the characters in cosmic games whose rules we're only beginning to understand. Whether we're living in a simulation or not, the questions it raises have already changed us. We can no longer take reality for granted or assume that consciousness is limited to biological brains. We must grapple with the possibility that our thoughts, emotions, and experiences might be patterns of information that could exist in forms we haven't yet imagined. The evidence continues to accumulate, the theories continue to evolve, and the technology continues to advance toward creating artificial consciousness that might be indistinguishable from our own. We stand at the threshold of discoveries that will either confirm our suspicions about the artificial nature of reality or reveal new mysteries about consciousness that we haven't yet learned to ask about. But perhaps that's the most beautiful aspect of the simulation hypothesis. It reminds us that consciousness itself is the greatest mystery, the deepest question, the most profound puzzle in existence. Whether we're solving that puzzle as biological beings in a physical universe or as digital entities in a computational cosmos, the search for understanding remains the most fundamentally human activity we can engage in. The simulation hypothesis has shown us that reality might be far stranger and more wonderful than we ever imagined. It has revealed that consciousness might be the universe's way of understanding itself, whether that universe is made of matter and energy or information and algorithms. It has demonstrated that the deepest questions about existence lead not to final answers, but to even deeper mysteries that challenge everything we think we know about what it means to be conscious, aware, and alive. In the end, whether we're real or simulated might matter less than the fact that we're here, now, thinking these thoughts, asking these questions, and marveling at the mystery of our own existence. The simulation hypothesis has given us a new way to appreciate the profound improbability and incredible beauty of consciousness itself, regardless of the substrate that supports it. We are the universe becoming aware of itself, whether that universe is physical or digital, natural or artificial, real or simulated. And in that awareness, in that capacity for wonder and questioning and discovery, we find something that transcends any distinction between what's real and what's not. we find consciousness itself, the most remarkable phenomenon in existence, regardless of whether existence is made of atoms or bits, matter or mathematics, reality or simulation. The question of whether we're living in a simulation has opened up new frontiers of understanding that will occupy scientists, philosophers, and thinkers for generations to come. Whatever the answer turns out to be, the journey of discovery has already revealed truths about consciousness, reality, and existence that have expanded our conception of what's possible in this strange and wonderful universe we call home.